All right. So, yeah, the plan is to start with a quiz, but I'll show, I guess, a little bit of mercy, and I'll start with allowing for 2 questions over homework. So, I said the quiz is going to cover 2.6 and 2.7, so you might want to ask me a question from 2.6 and then a question from 2.7, just so you can recall what it is we were doing in those sections. So, any requests? From 2.6, 2.7, number 6, 11. Okay. So we're looking at page 133, number 11. It says, if a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. So the first thing that I'm looking at is all my units to make sure, it's all in the same units. They're all in centimeters, so I'm happy about that. I'm going to draw a picture. I have a snowball. So I'm going to assume that a snowball is a perfect sphere. It's melting, so it's melting evenly. So it's going to stay a sphere the whole time. And I have basically 2 situations here. I have the general picture of what's happening, and then I have the instant in time that they're asking me about. So they want to know what's happening. It says find the rate at which the diameter decreases when the diameter is 10 centimeters. So I'm going to draw a diameter across this thing. At the instant in time they're asking, that's 10 centimeters. But in general, that diameter is changing as it melts. So I don't want to fix it at 10. I want to call it something else. I'll call it capital D for diameter. Make sense so far? Questions? Now let me write down what's given and then what I want to determine. And you don't have to do these in any particular order. It says to find the rate at which the diameter decreases. Rate means derivative, right? So the rate that the diameter decreases. So that's the derivative of the diameter with respect to time. That would be what I want, right? That's the speed of the diameter, the speed that the diameter is changing at. I want that at exactly the moment that the diameter is 10 centimeters, right? And I'm given what? Okay, the rate, what's decreasing at? The surface area, right? So I'm given the change in area with respect to time. Now, I could use SA for surface area. I'm just going to use A, and we all understand that's the area of the sphere, right? That's what I want. And that should be all I need to get going here. What's the next thing you do after you write down what you're given, what you want, after you draw your pictures? What do you need to come up with? An equation that connects what to what? dA, which is the area, right? I need to connect the area to the diameter. So do we have a formula that connects the area of a sphere to its diameter? So I go back to my formulas. And the only formula I have in the book says under sphere that the area of a sphere is equal to 4 pi r squared, right? 4 pi r squared? That's the only formula I have. However, I know the relationship between radius and diameter, don't I? I mean, we all should know that If you take twice the radius, you get the diameter, right? So if I solve this for radius, the radius is half the diameter. I mean, that's another way of saying the same thing, right? So I could come back to this formula, area equals 4 pi, but instead of r squared, I could put 1/2 d squared. And then go ahead and square 1/2. 1/2 squared is 1/4. That 1/4 will multiply times the 4 out front and go away, won't it? And you'll just have pi times diameter squared. That make sense? Square the 1/2. That cancels out the 4 in front. Then you do have to square the d, so you get d squared. So now I have a formula, don't I? An equation relating the two variables that I want to try and find derivatives of. So what do I do with that equation? What do y'all think? Plug in? Diameter? Not yet. You must do what first? Differentiate. Okay? Remember, the order that we do that's important. You don't stop the snowball from melting, right? You don't stop it and then say how fast is it changing. You take the derivative, treating the diameter like a variable, and then after you find the derivative, then you go say, okay, I'm going to stop it and plug in 10 for d. So what is the derivative of this? dA dt is the left side. Good. Pi is a constant, right? So pi, what's the derivative of d squared? 2d chain rule times d dt. Y'all remember the DDT? It's a wrestling move, isn't it? I used to do that to my brother all the time. DDT. Any questions on how d squared becomes 2d dt? No? Okay, now what we wanted in the problem, right? The question was, what's dt, right? That's what we wanted to know. So I'm happy that it appears here. Do I know dA dt in the problem? That's part of my given, isn't it? Oh, wait, hold on. Do I have this backwards? Oops, I said it the wrong. Why did I put question marks on both of those? Why didn't y'all say something? Okay. dA dt, see how I put the question mark there? Actually, that's not a question. What was it in the problem? What was it? 1 centimeter squared per minute. Okay, sorry about that. I accidentally wrote a question mark there. So we do know dA dt. We want to know dd dt. And do we know what d is? 10. See, now we can plug in the 10 at this point. So we should just be able to plug everything in. I'm going to plug in 1 equals pi times 2 times the diameter, which is 10, times dd dt. Oh. How do I do this? Is that okay? One divided by 20 pi. Equals dd dt. And we'll go ahead and figure out what that is on a calculator. We'll just get a decimal approximation. And then divide 1 by that. And you should get something like 0.01592 is approximately dd dt. And how is this measured? How do you measure this quantity? I mean, that's a speed, right? That's a speed that the diameter is changing. The diameter is measured in what? centimeters, right? And time is measured in minutes here, right? So this should be the unit next to this should be centimeters. Ooh, that's too thick. Centimeters per minute. Does everybody have their formula sheets that have the different shapes on them? Because you're going to need it today. If you don't have them memorized, then you'll need it for the quiz. Okay, anything else out of 2.6? I won't do another 2.7 one. 2.6, number 11. All right, good one. So this is page 127, number 11. We have tangent of x over y equals x plus y. And you're supposed to find dy dx. That means that we treat x like our independent variable. We treat y like it depends on x. So anytime we take derivative of like x, it would be 1, but anytime we take derivative of y, it would be y prime, right? So on the left side of this equation, here I come with my differentiation. I have to use what rule on the left side? Chain rule. And then inside the chain rule, I actually have what? Quotient rule. So let me start with the chain rule. What's the derivative of tangent of something? Secant squared of that junk, which is x over y. Now times the derivative of what's inside. So derivative of what's inside, I'm going to use a quotient rule, right? You don't just take derivative on top and bottom, right? Someone's not going to do this, 1 over y prime, right? Derivative top and bottom separately. That is not what you do. Quotient rule says derivative of the top times the bottom minus derivative of the bottom, y prime times the top, all over bottom squared. That completes the differentiation on the left side. On the right side, you have equals what? 1 plus y prime. Okay, so let me try and clean this up. I have secant squared x over y times here. How about this? 1 over y minus y prime x over y squared equals 1 plus y prime. What did I do there? I just separated this, right? I took that and I just separated it into two fractions. I had y over y squared, which became 1 over y. And then I had y prime x over y squared, which is the other side. Now, the reason I did that is because I'm trying to get y prime by itself, right? Trying to get my y primes together on one side of the equation. Before I can do that, I must distribute this whole thing through this parentheses. So I split what was in the parentheses into two terms so I could distribute it. Does that make sense? So what I get here is 1 over y. I'm just going to stick that in front of that secant, right? You cannot put that 1 over y in there with that x over y. And then I have minus y prime x over y squared secant squared x over y equals 1 plus y prime. So all I did was just distributed, right, the secant squared through. Now I'm going to move all my y primes to one side and everything that doesn't have a y prime to the other. I'm actually going to move the y primes to the right because I have a minus on that y prime there. So when I move it to the right, it'll become a plus. That's just my preference. It wouldn't be wrong to go the other way. No. Oh, yeah, I'm leaving this one on this side. I'm going to bring the 1 from the right side to the left. I'm leaving the y prime on the right, but I'm bringing that other y prime over. Any questions on that algebra there? Just moving stuff around. And what do you do on the right side now? Factor out of y prime. So you're left with 1 plus x over y squared, secant squared x over y. And then on the other side, 1 over y, secant squared x over y minus 1. And finally, divide through. So divide everything, both sides of the equation, by that stuff on the in parentheses on the right side. And you could probably go further with this, but I'm going to stop here. I mean, like if you would check it in the back of the book, they might clean that up a little more. Hold on, let me finish writing this and make sure. Do what? Multiply y squared where? Like right here? Like right here? Multiply both sides of the equation by y squared? You could have done that. That's fine. See, that's what I would do at this point right here. I would actually multiply the top by y squared and bottom by y squared and distribute it through like that. So. But I'm not going to go that far. All right, I think that's sufficient for getting us started with the quiz. All right, anybody else? Last call? So the first problem on the quiz was very similar to number 7 on the homework on page 127. I just changed, the one in the homework is y cosine x. I made it x cosine y. And then instead of x squared plus y squared, I put x squared plus y cubed. That was the only difference in the problem. On number 2, well, that was on your formula sheet if you had it sitting in front of you. What? So the derivative of e to the x and derivative of natural log of x are on your formula sheet. And that's part of what you were supposed to watch with the videos for today. And then number 3, when I was at the funeral, I had asked y'all to watch those lectures from the fall. I did number 3 in those videos, but I did it backwards. I did, instead of asking for how fast the radius is increasing, in the video I said how fast is the volume increasing. So it was just switched. You know, the d, instead of wanting to know dr dt, like the quiz, the one I did in the video, I asked for dv dt. So, all right. I'm going to post the solutions to these later today. All right, when I post the video, I'll put out like the notes I usually do, and I'll put the solutions to the quiz out there. All right. So what is the derivative of e to the x? E to the x. And what is the derivative of the natural log of x? 1 over x. Those are two very important formulas to know today as we move forward. We do have some stuff here. Again, I'll post this later. Today we wanted to do a quiz, answer any homework questions, cover problems from 3.3 and 3.7. There's going to be no homework out of 3.1 and 3.2. If you watch the videos on those are really short. It was just to get you acquainted with what e to the x looks like, what natural log of x, what exponential and logarithmic functions look like when you graph them. But everything I said on those videos for 3.1 and 3.2, you should know. Okay, like everything I stated there, because it's very short and to the point, but those points you need to know. Then next time, you'll watch the videos for 4142. Those are the homework assignments for 3337. And then remember how I said I'm going to give you like a problem or two out of those word problems, so we keep on practicing them. There's number 27 and number 28 are two problems to do from related rates. All right. So let's get into what today is about. And that is 3.3, which is the derivative of exponential and logarithmic functions. So this is 3.3. Derivatives of exponential and log functions. So if you're looking for like a main formula, all right, of what this section is about, if you're looking for the main ideas, here they are. If you take the derivative of a constant, so a is a constant here, raised to the u. Now you can use like our junk. Remember how we've had junk in the past? So if you've got a number raised to something, the derivative of that is itself a to the u times natural log of a times u prime. Now there's a special case when that a is e. Now e is a very special number, right? If this is e to the u, then the derivative of e to the u is itself times natural log of e times u prime. But what is the natural log of e? 1. So this just turns out to be e to the u times u prime. So you could kind of say it like this. The derivative of e to some junk, right? The derivative of e to the junk is e to the junk times the derivative of the junk. Right? That's what it is. Now the quiz problem, right, so this is a little different. The quiz problem was what's the derivative of e to the x, right? Well, according to this formula, the one there in red, it's kind of hard to see that middle one's red, is e to the x times x prime. But what's x prime? 1. So we wouldn't write x prime. It would just be e to the x. And that's what makes e to the x such a great function. I mentioned this in the videos. E to the x is the only function other than the 0 function that is its own derivative. All right, now, so the black one up there is like the most general idea behind derivatives of exponential functions. The red one there is if you have e to some junk, and then the green one is if you have e to the x. With me? Okay, then we have the logs. So I'll do this one in black also. The derivative of log base a of some junk is 1 over the junk, natural log of a on the bottom, times the derivative of the junk. And a lot of times books will put the derivative on top, like this. Just slide it over. That's the general formula. If we use a specific base of the log, and the base that we love to use is the e, log base e is actually the natural log. So we would never write it that way. We actually would write this, natural log of u. Okay? So what is the derivative of natural log of u? It is u prime over u times natural log of e. But what is natural log of e? 1. So this just becomes u prime over u. Try and make this real quick. You see this log base e of u? Like if it was log base 2 of u, it could, there's all sorts of different logs. You can have different bases, right? 2, 4, as long as the number down there is positive, okay? You can have bases for logs. The reason why we use this notation, natural log of u, instead of log with the little subscript e, the only reason we do that is because back in the days before computers, when people used to use typewriters, they would have to use the natural log function. Always occurred, like it was always coming up in research and stuff. And so, you'd have some chemist who's doing all this work, and it's got a bunch of natural logs in it. And instead of, if you've ever had to subscript on a typewriter, has anyone ever used a typewriter? Have you ever had to subscript? You have to do a little half rotation of the drum and then type and then back, and it slows the process down. So what they did is they agreed that we would use this in the yellow here. We'd use that as like the shorthand notation. So that way you could just type and never have to stop and do that. But that's the only reason, okay? It's kind of a weird little fact. All right, now I'm going to do in green what we get when our junk is just x, right? So what's the derivative of log base ex? Well, again, we would never write that. We would write what instead? ln x. The derivative of ln x is x prime over x, right? Natural log e, but natural log of e is 1, so it's just x prime over x. But what's x prime? 1. 1 over x, which was the answer to the quiz problem. But again, that's a formula on your formula sheet. So in my opinion, every Cal 1 student should know that the derivative of the natural log of x is 1 over x. But it's more valuable for you to know that one in black, because then you can take the derivative of any log. With me? Okay, we're ready to do some examples now. So I'm going to be working off of out of section 3.3, and I'm going to start with number 2. The problem is f of x equals x natural log x minus x. Find f prime of x. So we are not going to use implicit differentiation. Remember implicit differentiation? That's what the quiz was over just a second ago. That's when your y's and x's were mixed up in an equation you could never solve for y. Here, you could almost look at this as being like y equals the right side, and the right side just has x's in it, right? So this is really asking for y prime. So it's just a straight derivative, treating x like the independent variable. So what do we see on the right-hand side here? I'm going to take the derivative. Y prime equals, what's going on the right side? Product rule. The product is happening right in between the x and the natural log of x, right? And then separated from that is minus x. So I can go ahead and take care of the minus x. I'll just throw it out here. What would I get if I took the derivative of negative x over here? Just minus 1, right? But I have to still do the derivative of the x times natural log of x, which is product rule. So what's the derivative of the first one? What's the derivative of x? 1 times ln x plus, now what's the derivative of natural log x? 1 over x times, finish off the product rule, x. And so what you get is natural log x plus 1 minus 1. Because 1 over x times x, right? 1 over x times x is 1. So this just turns out to be what? ln x. Natural log of x. So the derivative of x natural log x minus x is ln x. I've had students in the past that look at this right here, and they look at that. That's a lowercase l, but some people think it's an I, and they say INX. ln x comes from natural log. The way French would say that would be logarithmic naturel, something like that, backwards. So that's why it's ln and not nl. It makes more sense in English to be nl, right, natural log. But it's a French thing, all right? All right, let's move on. How about number 4? So we have y equals, no, it's f of x again. F of x equals natural log of sine squared x. So what rule or rules do you see here? Chain rule, right? If it's chain rule, then what's the last thing happening? What's the last thing that would happen? The outside function. The ln, right? Then go in, what would be the next thing that happens? Squared, and then inside that, the sine. So we have to remember that squared on the sine means that you would, like if you started by trying to plug in an x, the first thing you do is you take sine of it, then you'd square it, then you take natural log. So the backwards, doing that in reverse order would be natural log, then square, then sine, right? So when I do my chain rule here, I first say, what is the derivative of natural log of some junk? Natural log of junk now. It's not natural log of x, it's natural log of junk. So do I need to go flip back or no? It's 1 over the junk, which here is what? Sine squared x times the derivative of the junk now, right? The derivative of the junk. But what's derivative of the junk? So now you have to go inside, the natural log's gone. What's derivative of sine x squared? So what's the derivative of junk squared? 2 sine x to the first power, but I don't need to put first power, right? So I've taken care of the natural log when I did this step. I took care of the squared part when I did this differentiation. And now I need times the derivative of what? The sine, which is cosine x. Does that make sense? And clean it all up. I have 2 sine x cosine x over sine squared x. And you might recognize 2 sine x cosine x from pre-cal. What's 2 sine x cosine x? It's a double angle identity. It's sine 2x. Not sine squared x, sine 2x. I didn't have to do that, but it looks a little cleaner, doesn't it? Questions? Sure? How about number 8? Or, you know what? Yeah, let's do 8. So f of x equals log base 5 of x times e to the x. All right, so we have chain rule here, right? We have log base 5 of junk. The junk inside is a what? It's going to turn out to be a what when we take its derivative? That's right, product. It's x times e to the x, right? So that's going to be a product rule. But I first need to figure out what's the derivative of log base 5 of something. What's derivative of log base 5 of something? 1 over the junk, right? The something. And then this is important right here. ln 5. Good. Now, natural log of 5 is just a number, okay? Think of it as a constant. It's like 2, but it's not 2. It's natural log of 5, whatever the hell that is on your calculator. Okay, so I have 1 over x e to the x times natural log 5. That's the derivative of log base 5 of some junk. Times, chain rule, go inside. What's the derivative of what's inside? That's a product rule, right? So I have derivative of the first one, which would be 1 times e to the x plus the derivative of e to the x, which is itself times x. Which is e to the x plus e to the xx all over x e to the x times natural log 5. Kind of running out of room there. I just took everything in parentheses, moved it up to the numerator, just cleaned it up a little bit. There's something else we could do here that I'm sure the book does. Couldn't you factor an e to the x out of the numerator? They both have e to the x in them, right? So you can make that 1 plus x. And then on the bottom you have x times e to the x times natural log 5. So what can you do now? Cancel the e to the x. Because this e to the x, this e to the x cancel because there's multiplication on the bottom, right? So you can cancel through. Can y'all see that all right back there? So I'm left with 1 plus x over x times natural log 5. You'll notice, maybe you won't notice, I don't know. My pages are going to be coming to an end here. I'm trying to make it where what I'm writing on will print out better for y'all. You know how sometimes when you print out the stuff I do here, it like carries on to the next page, if you've noticed that? I'm making it so it should print off nice and even now. Okay, questions on that one? Want to try and get, oh, this one looks good. Capital H of z equals natural log of the square root of a squared minus z squared over a squared plus z squared. So my variable in this problem is z. A is a what? Is a constant. A is a constant. What rule do you see happening here? Chain. What would the last thing happening be? ln would be the last thing. Okay, what would be the next thing? Square root and then quotient rule, right? So I could do it that way. However, would you agree that this is the same thing? I'm going to save myself a lot of work here. Isn't the square root the same as raising it to the 1/2? Yes? And then there's a property, because this was mentioned, I think, in 3.1 or 3.2. In 3.2. There's a property of logs that says this, and I'll just write it down. Natural log of x to the n equals n natural log x. That's something that in college algebra, hopefully you saw, that if you ever had natural log of something to a power, that power could come out in front. Do y'all remember that? A very nice property of logs. So as an example, natural log of x cubed is the same as 3 natural log x. So for us, the natural log of all that junk to the 1/2, what can I do with that 1/2? Pull it out front. And that's just going to make our differentiation a little bit easier. The 1/2 comes out. Now we have natural log. Then we have the quotient rule in the natural log. But do you see that we're not going to have to worry about the square root in our differentiation? Like it's no longer part of our chain rule. It's really a 1/2 sitting out in front, which is really, really good. Okay, I think now I'm ready for the derivative. The derivative, h prime of z, will be equal to, well, the 1/2 is a constant, so I'm just going to leave it 1/2, times, what's the derivative of natural log of some junk? 1 over the junk, right? 1 over that junk. Okay, times what? The quotient rule on the junk, right? Quotient rule on the junk. So here comes my quotient rule on the junk. I mean, I'm kind of like already setting up my quotient rule right here. So remember that what we're trying to take derivative of, I just highlighted in yellow, is the quotient rule on that. Treating a like a what? Constant, and z like the variable. So let's do quotient rule. Derivative of the top. What's the derivative of the top? What's the derivative of a squared? 0. 0. Because a is a constant. So that may as well be 4 squared. And what's 4 squared? 16. What's derivative of 16? 0. So we treat the a like a constant. The derivative of it will be 0. A squared. That all right or not? Does everyone understand, by going back and looking at the problem, the fact that the z is in there like that tells you what the variable is. And I told you previously that we usually treat a, b, c, and d like constants. Okay, so the derivative of a squared is 0 minus what's the derivative of z squared with respect to z? Just 2z, right? 2z. So I'm going to get a minus 2z. That's the derivative of the top, right? Times the bottom. Okay, minus the derivative of the bottom. What's the derivative of the bottom? 2z times the top all over the bottom squared. Now I am going to clean this up. What about this? What's 1 over a fraction? It just flips the fraction over, doesn't it? Okay, so this becomes, I'll just leave the 1/2 out here for now. This becomes a squared plus z squared over a squared minus z squared times, now I'd like to distribute the negative 2z through, and I'd like to distribute the negative 2z through again. So I should get negative 2za squared minus 2z cubed minus 2za squared plus 2z cubed. Just be careful with your signs there. All over a squared plus z squared squared. We do get cancellation, right? The 2z cubes are gone. How many za squareds do I have? Negative 4, right? Negative 4. Negative 4za squared over a squared plus z squared squared. Anything else? A squared plus z squared, like this right here. There's one of them, right? And then there's two of them down there. So I can cancel one of them out and then cancel one and just be left with one of them. I can also reduce the 4 and the 2, right? So my new numerator is negative 2za squared over what's left on the bottom. A squared minus z squared times a squared plus z squared. Hey, isn't that a to the fourth minus z to the fourth? Right, like if I were to write x plus 2 times x minus 2, you would say that that's x squared minus 4, wouldn't you? That's a difference of squares factored over there in the top right. I'm just doing that here. I'm kind of saying like x minus 2, x plus 2, right? So it should be x squared plus 4. So that is a difference of squares factored. Y'all agree or not? Now, if you would have just gotten it to here, I wouldn't take off for that. I'm just pointing it out that, that's probably what the book has. Questions, comments, concerns, gripes? Okay, let's try something else. Yes. Sure. Because 1/2 was being multiplied in front of a function. It was not 1/2 by itself. Like if I write 1/2 plus x and I say what's the derivative, you would say 0 plus 1, because the derivative of 1/2 is 0. But if I say what's the derivative of 1/2 times x, right, or 1/2 x, your answer would be 1/2. Because what you do is you carry the constant with you and you take derivative of x. That 1/2 was being multiplied times the natural log, so we carried it. Okay, I'm just picking another problem here. I'm going to just make one up. Okay, y equals 7 to the sine to the third of 5 to the x plus x. So what do you see happening here? Chain rule. What's the last thing happening? Anytime you want to try and figure out what's happening last, just imagine you plug a number in for x. So if you plug in x, right, the first thing you would do is figure out everything in this parentheses, wouldn't you? Let's say I'm plugging in 2. You do 5 squared plus 2, wouldn't you? Then you would do what? After you figure out that number, you would do what? Take sine of that number, right? And then you would do what? Cube that number. And then what would you do? Take 7 and raise it to that answer, wouldn't you? That's the order of operations in doing that. So going backwards, the last thing happening was the 7 to a power, isn't it? 7 to junk. So we need to ask ourselves, what's the derivative of 7 to junk? So what's the derivative of a to the junk? A to the junk. So this will be 7 to the junk, right? Won't it just be itself? But then times, very important here, ln of 7. And that takes care of the derivative of 7 to the junk. But then chain rule says you now need to multiply that by what? The derivative of the junk. So good. 3, because I'm taking care of the cube now, right? 3 sine squared of 5 to the x plus x. So now we've taken care of the derivative of something to the third power. Chain rule says keep going, times, now what was the next thing? The derivative of, we did the cubed, we haven't done the sine yet. What's derivative of sine of something? Cosine of it. Still chaining along here, times, finally, oops, I'm running out of room here. Times, now we're done with the sine, so inside, what's the derivative of, well, you have 5 to the x plus x, right? That's a sum, so you can do them separately. What's derivative of 5 to the x? 5 to the x. Isn't 5 to the x like a to the u? Times ln of 5 times 1, but you don't need to put that. Then plus what? 1. Okay, now I'm kind of out of room here. See, what happened here is derivative of the 5 to the x. The derivative of that is this part right here. And then the derivative of x is that 1. So the derivative of 7 raised to the sine cubed of 5 to the x plus x is 7 raised to the sine cubed 5 to the x plus x times natural log 7 times 3 sine squared 5 to the x plus x times cosine of 5 to the x plus x times 5 to the x times natural log 5 plus 1. That's big time chain rule right there, right? There's a lot happening.
So the ln5 is from the a to b.
That's from the formula for this. The derivative of a to the u is itself times natural log of a times u prime. Now the u prime is really just like the continuation of the chain rule, because your u prime may turn out to be another chain rule. But the natural log of a is just a constant that always needs to appear there. Okay? Very good question. Very good question. Let me illustrate this a different way. All right? Because we're about to head into this direction anyway. The derivative of x squared is what? 2x. So what happens was the 2 came down, we did x, we subtracted 1 from the power, we got 2x to the first power, right? That's because we were working with something that looked like this. Our variable raised to a number, right? Variable raised to a number, we get nx to the n minus 1. The important thing here is that this is our variable and this is a number, right? If it's the other way around, 2 to the x, all right? The derivative of this is not, okay, is not x to the 2 to the x minus 1. You don't bring the power down and subtract anymore. That is not the case. What you do is use the formula I gave you. It's 2 to the x. It's itself natural log 2. And that's using the fact that a to the x, the derivative of a to the x, is itself natural log a. Does that answer your question? And here we have the number, and here our variable is here. So you see in the top one, it's backwards than the bottom one. In the top one, your variable is the base, a number is the exponent. On the bottom one, your base is the number and your exponent is the variable. Totally different formulas for each of those cases. All right. I think the rest is just kind of fun for you to try and figure out. You're just going to have to play with these. And you get the gist of it, though? The homework assignment for that's pretty in-depth, so and there's a lot there. Now, we're going to get into something that's really, really nice. It's called logarithmic differentiation. Logarithmic differentiation. So I'd like to motivate this whole idea by an example. All right, like what the heck is this going to be? Let's start with this classic example right here. I'm still in 3.3. Okay. Logarithmic differentiation. Here's the problem. Find y prime. What do you notice is an issue here that we have? Yeah, there's two x's. See, if that was x squared, I'd be fine, right? It'd be 2x. If it was 2 to the x, I'd be fine, because then the derivative would be 2 to the x natural log 2. So I have ways of dealing with it when one of those is a number, right? Either the exponent or the base. But I have no way, up to this point, we have no way of dealing with it if your variable appears in both the base and the exponent, right? So notice variable, your variable appears down here, and you have a variable also up here. And that's pretty much like, oh, what the hell do we do? Well, we do what's called logarithmic differentiation. And it uses the power of that property of logs that I put up on the board earlier, where you can pull the power out front. Remember that? Okay, the n came out in front. We're going to use that power of the log to figure out the derivative of this. So the first thing I'll do is I'm going to take the natural log on both sides of this equation. That's why they call it logarithmic differentiation, because you're going to do a derivative by using a logarithm. Logarithmic differentiation. So I started out with that equation on top, right? Y equals x to the x. And working with the equation, I can do the same thing to both sides of an equation, and it's still the same, right? It's like you have an equation x equals 2, you multiply both sides by 2, stays the same. When you take log on both sides of an equation, it stays the same. So nothing has changed yet. What am I trying to get at again, though? I'm trying to find y prime, right? Okay, keep that in mind. I'm going to now, though, take that x and pop it out. So I'm using that property that if you have x, natural log of x to the n can pop out. All right, that's what I'm using. Very, very nice formula. Property of logs. So I'm treating that x like it was a power, right? And I'm pulling it out in front. Is that all right? We're okay with this? Now, don't I have an equation that has x's and y's in it? Right? I mean, I have an equation that has x's and y's. Can't I do this now? What was my little squiggly line representative of? Implicit differentiation. Implicit differentiation. Right? That's what the quiz we just did was over. So remember, I want dy dx, right? That's what I want. Y prime was dy dx. So look at the left side of that equation and very carefully tell me what the derivative of natural log of y is. So what's the derivative of natural log of u? 1 over u not you, sorry. So for us, it would be 1 over y, but then times the derivative of what's in there, right? What's the derivative of y? Y prime. Does everyone see that the derivative of a natural log of y is 1 over y prime? No one has a question? That's the left side. There's nothing else to do on the left. What about the right side? What do you see happening over here? Product rule. So what's derivative of x? 1 times ln x plus what's derivative of ln x? 1 over x. And we don't have to put x prime, right? Times x. So we get 1 over y prime equals natural log x plus 1. And what was the goal with implicit differentiation after you take derivative? You wanted to do what? Get y prime by itself. So how can I get y prime by itself over there? Divide by 1 over y or multiply both sides by y. I'm going to multiply both sides by y. And when I multiply, it has to distribute through, right? So now that is correct, but didn't we have earlier in the problem, we had an equation that told us what y was? Remember this equation up here? It said y was equal to x to the x, didn't it? So what I can do here is I can actually come in and replace these y's with what it's supposed to be in the problem. So it should be x to the x natural log x plus x to the x. The advantage of the second answer is that if you want to know the derivative, that means you want the slope of the tangent line. All you have to give me is an x, and I can give you the slope of the tangent line. As opposed to this one on the left, you would have to give me the x and the y. Y'all see how that works? Logarithmic differentiation. It's a really, really nice technique. I'm going to do probably one more of these, and then I'm going to give you a couple of problems to work on, and we'll take a break afterward, all right? So y'all can sit here and watch me do this all day long. It doesn't mean anything until you sit down and try it, right? Y equals e to the negative x cosine squared x all over x squared plus x plus 1. So before I begin this, let's make sure we are all clear with the fact that we could do this using quotient rule. Right? Don't we have a quotient? And the numerator is actually going to be, how would you take the derivative of the numerator? Like when you tried to set up that f prime g minus g prime f all over g squared. When you do f prime, you would have to do a what? A product rule, and then one of those, cosine squared, is a chain rule. It's kind of a mess, isn't it? Kind of a mess. So what I'm going to do is use logarithmic differentiation. So logarithmic differentiation says that you should take the natural log on both sides of the equation. So let me take natural log of the left and natural log of the right. Now, in the last problem, what was the bringing the log in on both sides? What did it allow me to do? I mean, what was that critical next step that I was able to accomplish? Yeah, I was able to get that x and drop it out, right? That x was able to drop out. Here, I don't have that, do I? But there are some other properties of logs that, again, were in my videos that I did. One of them said this. Actually, I have my notes with me so I can tell you exactly what I'm talking about. It's written a little different in the notes. I'm talking about 3.2.3 in the notes. Property 2 says log base A of x over y equals log base A of x minus log base A of y. So it says anytime you have a log and you have a fraction, you're allowed to take it and split it into two logs with subtraction between them. Again, this is a college algebra topic. So can't I treat this whole numerator like x and the whole denominator like y and split it into two logs using that property? So watch my next line. I have not taken any derivative yet. It's going to turn to natural log of e to the negative x cosine squared x minus natural log x squared plus x plus 1. How's that? Any questions there? Now in my notes there's another property that says that log base A of x times y is log base A of x what? Plus log base A of y. So do you see in this first natural log with the e to the negative x, do y'all see multiplication between the e to the negative x and the cosine squared? So can't I split that into two logs? Right? Natural log y equals natural log e to the negative x plus natural log cosine squared x minus natural log. Now, can I split this one up? The x squared plus x plus 1? Can I split that into three logs? No, because it's addition, right? You have addition between those terms. The property only works if it's multiplication. So you can't split that one. So we're kind of screwed with that one. Anything else? Does anyone see anything else we can do? Absolutely. The 2 here is really squaring the cosine, isn't it? So that's like a power on the cosine that can be pulled out in front. There's also something I can do in that first one, natural log of e to the x, e to the negative x. I can bring the the negative x out front in front of that, right? I have natural log y equals, it is going to just be equal to, it's just going to be equal to negative x. Because natural log and e are inverse functions, they'll kill each other off. So really, there's two ways to look at this. Natural log of e to the negative x, either they wipe each other out and you can just get negative x, or if you want to look at it this way, the negative x comes out in front and then natural log of e is 1. Either way, you get negative x. But I left it in there to show some of the work here. 2 natural log cosine x minus natural log x squared plus x plus 1. I'll go one more line. So I'm just going to make this a negative x plus 2 natural log cosine x minus natural log x squared plus x plus 1. All right. Questions? Y'all never have questions. No one ever asks me. Now, I think now I'm ready to differentiate. Because what I'm doing is I was cleaning everything up to the point where I was happy with it. So I'm going to get up just because I'm tired of sitting already. Look, when I look at this, when I was here, I didn't want to take a derivative. Here, this was still some chain rule involved here, right? Like you have natural log, and inside that you have squared, and inside that you have cosine. And then on this one, well, there's nothing I'm going to be able to do there. But if you have properties you can use them. exploit those properties. So I bring this all the way down to a negative x. Derivative of negative x can be what? Negative 1. Plus 2 times something. So I'll bring the 2 down. What's the derivative of natural log of something? 1 over that something times. Then go inside. Derivative of the something would be what? Negative sign? Okay. So I'd be done there. And then over here, minus natural log, derivative of natural log of something is 1 over that something times derivative of what's inside. So this is going to be to me, this is a much easier derivative than that quotient rule in the beginning that would have required some product rule, and then in that product rule there was some quotient, there was some chain rule. All right, now what's the derivative of the left side? 1 over y times y prime equals negative 1 plus 2 times 1 over cosine x times derivative of that, which is negative sine x, minus, not natural log, 1 over x squared plus x plus 1 times derivative of what's inside, 2x plus 1. I'm going to clean that up. Sine over cosine's tangent, right? And it's negative, so negative 2 tangent x. And then minus 2x plus 1 over x squared plus x plus 1. And then I'll multiply both sides by y, right? So I'm just going to do it this way. I'm just going to throw that y out in front of all of them. And that would be okay, but did we have an equation that had y in it? Way earlier in the problem. Wasn't the original problem y equals something? All that? So I could come down here as my final answer. Y prime equals e to the negative x cosine squared x over x squared plus x plus 1. That's y, right? That is y? Yeah. Times, in parentheses, negative 1 minus 2 tangent x minus 2x plus 1 over x squared plus x plus 1. I'm at the bottom of the page. All I do is replace the y with what y was in the original problem, right? Are there any questions? Okay, what I'd like for you to do right now on your own is I'd like for you to do page 169. Let's do number 9. Number 25. And number 57. So this is just exercise, okay? When you're done with these, take a break. Let's say that I'll give you 15 minutes to do these problems, which puts us at about, what, 2:50 and a 10-minute break. So we're going to say 3 o'clock is when we are going to continue class, all right? It's 2:36, 2:37 right now. 3 o'clock we'll resume. So try and get your 10-minute break in there somehow. Okay, that pretty much does it for 3-3. We're skipping over 3, 4. It's exponential growth and decay. And 3, 5, I'll talk about next class. 3, 6, I'll talk about next class. We're going to go right to 3, 7. So 3, 7. L'Hôpital, yep. Okay, this section is called Indeterminate Forms and L'Hôpital's Rule, or LHospital. It's pronounced L'Hôpital. So the big thing right now for you to understand is we are going to revisit something we've kind of put away a while ago. Limits. Okay? We did limits, right? That's the way we pretty much started the class. I told you, to me, Cal 1 starts at the limit. So we did some limits, we did some stuff, we came up with this idea of the derivative, right? And then I gave you these rules, and that's what we've been doing, right? All the product rule, quotient rule, chain rule, and then all this other stuff. Implicit differentiation, logarithmic differentiation now. We saw how we could use it to do some word problems. That's what we've done. Now we're going to go back, and we're going to look at limits again. And we're going to first talk about what indeterminate forms are, and then I'm going to introduce you to a very, very, very nice rule called L'Hôpital's rule. So what are indeterminate forms? If in the limit you get 0 over 0. Remember this? This was like one of the first things that we ever kind of stumbled across with limits, right? We said, oh, the numerator's headed to 0, the denominator's headed to 0, right? So when I put there, if in the limit, this is so important that I'm saying this, in the limit, as you take the limit of something, you get something that looks like 0 over 0. That's what we call an indeterminate form. We can't tell you what the answer is until we do what to it? What did I always tell you to do once you had 0 over 0? Some sort of algebra, some sort of trick, right? But we may or may not be able to get an answer, but I can't tell you right off the bat. If it's 0 over 0, I can't tell you. I can't determine the answer just by looking at it. I have to do something. So it's indeterminate. What's another type of form that we saw where we had the same thing? Yeah, infinity over infinity. That was another indeterminate form. And you can even put plus or minus on both of those. So like you could have positive infinity over negative infinity, or the other way around, negative infinity over positive, or positive positive, or negative negative. It doesn't matter. Those are still indeterminate forms. The numerator is getting huge, denominator is getting huge. Who wins? Well, we have to do something to figure it out. What are some other things we ran into where we couldn't quite tell? We had fixed over 0, but that one did give us 3 answers, didn't it? It was 3 possible things. Remember that? Fixed over 0 gave us either infinity, negative infinity, or does not exist, right? So let's hold off on that one. Anything else? Fixed over infinity, that went to 0. Remember, anytime you had fixed and the denominator gets big, That went to 0. So that we could determine, right? The answer was 0. There you go. Infinity minus infinity. Right? What's infinity minus infinity? Don't know. Right? Don't know. Those are the things we've seen, right? Anything else that we've seen? I'm thinking out loud here. I don't think there's anything else. Oh, well, no, we didn't see that. Okay. So I think underneath each of these, maybe give you an example. Okay, I'll give you an example. Anyone else need to sign in? I'll give you an example of each of these. How about limit x goes to 0 sine x over x? That equals 1, right? Because I told you it does, right? But isn't that giving you the form 0 over 0? Okay. How about an infinity over infinity? Something like limit x goes to infinity, x squared plus 1 over 3x squared minus 1. That goes to infinity over infinity, right? Remember how you would do that one? Divide the highest power of x out. Okay, good. And then something like this. Limit x goes to infinity, square root of x minus x. You had a quiz or test problem that was like that one. Again, infinity minus infinity. And the way we did that one was we factored out like a square root of x and then made it multiplication. Okay, so that's just me reminding you of some of the things that we've seen. Now I'd like for you to consider some other forms that we have not looked at that are also indeterminate forms. So here are the new ones. 0 raised to the 0. Now let's consider why that's an indeterminate form. And I'll put an example below it. Limit x goes to 0 of x to the x. Now what's the problem with that? I mean, why is this an indeterminate form? The base, right? The x is the base, right there. That wants to be 0, doesn't it? It's trying to go to 0. But then you're trying to raise it to the 0. What is anything raised to the 0 supposed to be? 1, right? So the power is trying to turn the answer into 1, but the base is trying to be 0. So it's like this tug of war. Do y'all understand that? So you can't just look at that and be like, oh, it's 1 or oh, it's 0. It may turn out to be something completely different. Just like 0 over 0, we couldn't tell. Okay, so that's a new indeterminate form, 0 to the 0. Here's another new indeterminate form. 1 to the infinity. So here's an example of this. Limit x approaches 1 of x to the 1 over 1 minus x. And let's say x from the right, just so I'm technically correct. What does the base of that want to be? What does the base of this want to be? Where is x approaching? 1, right? So it's getting closer and closer and closer to 1. Now, is it actually ever getting to 1? No. Now let's talk about the exponent. What is the denominator of that exponent right there? It's going to 0, right? So you have fixed over 0. Fixed over 0 is going to wind up going to infinity, right? You know what? I need to change something. Flip the order. X minus 1 instead of 1 minus x. So what would happen here with our exponent, the bluish part, is that it's fixed over 0, and if you did that work, you'd realize that that goes to infinity. So you have something that's trying to be 1 raised to something that's trying to be infinite. So when you take a number that's a little bigger than 1 and start raising it to powers, shouldn't it try and get bigger? Yes? Like take the number 2 and start raising it to higher and higher powers. It gets huge, doesn't it? So get closer to 1, like 1.1. Well, if you do 1.1 raised to a big number, it's going to get big. So the base, the yellow, is trying as hard as it can to be 1, and the exponent's like, no, I want to rip you apart. I want to blow you up, right? Do you see that? It's, again, a tug of war. Do y'all follow this or not? I mean, it's kind of abstract, but how about this one? Infinity to the 0. What's the problem there? Without me giving you an example, what do you think the issue with that is? Yeah, the base wants to be huge, right? Like, let me become infinite, but the exponent's like, wait a minute, hold on. I like to turn things into what? 1. So who wins? You see the kind of the conundrum, the problems we have here? Let's see. Trying to think if there's any others. Can you all think of any others? Can you all think of anything that might cause an issue? Hold on, let me go with the first one I heard. 0 or infinity times 0. That's a good one. Because what happens is the factor on the left wants to become huge, right? But the factor on the right wants to become small. Do you understand why it's so important for me to have set up here in the limit up there? Because I'm not saying 0 times infinity is something we don't know. I'm saying something that gets huge times something that gets small we don't know. I say this because I had a student years ago who called me 2 years after Cal 1 and was like, you told me that this, and I was like, I never told you that. I said, when you take a limit and you get something like this, that's when this happens. You know, if I just say right now, what's 1 billion gajillion gazillion gazillion raised to the 0? What's the answer? 1, okay? That's different. A number to 0 is 1. But infinity to 0, that's an idea. That's a concept. All right. So we don't know who wins 0 times infinity, or doesn't even matter. It could be positive or negative infinity. That doesn't matter. Anything else? One raised to infinity. But see, 1 raised to infinity, we don't even know what that does. And then you raise it to 0, you still, yeah. I mean, so that would be like 2 of these together. We're trying to get the most basic forms that we could get, and then of course they get more complicated. What I've found in the past is that students kind of think that everything that has zeros, ones, and infinities works. That's indeterminate. Let me put some down here. Oh, new page. Let me put some down here and see. How about infinity to the 1? So the base wants to do what? Get huge, right? What does raising something to the 1 power do? It just leaves it alone, doesn't it? 4 to the first power is 4. So the base is I want to become infinity, and the exponent's shit, go ahead. That's what I want you to be. I want you to be whatever you want to be, right? That's what I'm going to let you be. So there's no conflict here. The answer to this would be infinity. Do you see? How about infinity to the infinity? Base wants to be big. Exponent wants to make it go there faster, right? No problem. So infinity. Trying to think of different ones that students will turn into problems when they're not. 0 to the 1. What does the base want to become? 0. What does the exponent want to do? Just leave it alone, right? Let it be. It's fine. So the answer to that one would be what? That would be 0. This one would go to infinity. This one would go to infinity. How about this one? 0 to the infinity. What does the base want to do? Get small, right? Go to 0. What does the exponent want to do? Be careful here. You think huge, right? But you have to kind of understand the properties of numbers between 0 and 1. Like if I take a number out here, it's like 2, right? And I start raising that to bigger powers, it gets bigger, right? 2 squared, 2 cubed, those get big. But what if you take a number like 1/2 and you raise it to, like, what if you square 1/2? It gets smaller, right? What if I cube 1/2? 1/8 gets smaller, right? In fact, if you pick numbers, any number between 0 and 1 and raise it to a power, it gets smaller. There's this misconception that, hey, if I give you a number and I say square it, everyone thinks, oh, it gets bigger automatically. That's not true. If you take a number between 0 and 1 and square it, it gets smaller. So when that base is trying to get small, the exponent comes and starts raising it to higher powers, and it actually gets smaller faster. So that one would go where? It would go to 0 extremely fast. So all these in blue here are not indeterminate forms. These are things we know the answer for. We already knew this. Infinity times infinity is infinity, right? Yeah, that's that commercial. I feel like I'm okay. Infinity plus infinity is still infinity, right? All right, so maybe we'll stumble across some others where you think they're bad, but the ones that we are interested in are the ones that I showed you before here. Let me see here. These are our indeterminate forms right here. Okay? And I don't have them memorized. I just think about them. You know, what's 0 to 0? Well, you know, like I'm explaining it to you is the way that I think about it. So you don't really need to memorize as long as you understand like how numbers work. Full page. All right. So that leads us to L'Hopital's rule. Okay. L'Hopital. Shit. This rule is fabulous. L'Hopital was a mathematician. He didn't do a whole lot as far as like great mathematicians are concerned. Like he's not Isaac Newton, okay? He's not a lot of mathematicians, but this rule that he came up with is super powerful, super useful, and one of the harder theorems to prove in calculus is this one right here. So here's what we're just going to come up with his result. L'Hopital said basically, if you're ever taking a limit, okay, and it doesn't even matter, x is going to, does not matter, okay, x is going to a box. It could be going to 2, to 0, to infinity, to 1, it doesn't matter. X is headed somewhere. And you have f of x over g of x. So you've got two different functions, right? Maybe the top is sine x, maybe the bottom is x. Maybe the top is x squared minus 2 and the bottom is something else. But you've got a fraction, right? If that limit goes to, so the arrow means that limit goes to infinity over infinity, positive or negative, doesn't matter, or 0 over 0, which were the first two that we really ever ran into, right? L'Hopital says if you ever get limits that look like this, then if the limit exists, it's equal to, so he's saying, look, if you ever get infinity over 0 over 0, then if there is an answer, okay, if you can get an answer, instead of looking at that limit, you can look at this one. The limit as x goes to 0, or x goes to something, of f prime of x over g prime of x. So somehow there's a very, very strong relationship between the function f divided by g and how that behaves compared to how their derivatives behave as a quotient. This is not quotient rule, though. Do y'all see that? Like, we're not taking quotient rule. We're just taking derivative of top and bottom and comparing that and finding a new limit and seeing if we can get an answer. So if there's an answer to the top one, it's the same as the answer to this one. So let's see how this is going to work, okay? First example. Limit x goes to 2, x squared minus 4 over x minus 2. Okay, this is one of the first limits that we ever did in this class where we were looking at it saying, okay, everyone, let's plug 2 in and let's see what we get. And I said, draw a little arrow, show me what's happening. So plug 2 in, what do you get? 0 over 0, right? Now, how would we do this before L'Hopital? What would you do to that to figure out that limit? Some algebra, right? What algebra would you do on that one? Factor the difference of squares on top, right? And then you would cancel it. Remember that? Okay, but screw all that now. 0 over 0 is an indeterminate form. And L'Hopital says that if you want to try and figure out that limit, all you have to look at is this new limit. Now, there's two different notations that books use usually to let you know, to let the reader know they are applying L'Hopital's rule. A lot of books put a little h over the equal sign, an h over the equal sign. So what I'm saying is that that limit up there is equal to this limit by L'Hopital's rule, by putting the h there. I don't do it that way. I put an L and I circle it. And I'm not sure if I saw that in a book or I just did that wrong once and just kept doing it for the rest of my life, but that's the way I do it. All right, you can do an H or an L, but you have to do something. You can't say that limit's equal to that because they're not always equal. It has to be 0 over 0 or infinity over infinity for that to work. Okay, so limit of, now L'Hopital says all you have to do is what? Differentiate the top and bottom separately, right? No quotient rule, just take derivative of top. What's the derivative of top? 2x over 1. Now plug 2 in, and what do you get? 4. Done. And if you check it, okay, if we were to go back and do it the old school style, the way we did it before L'Hopital's rule, right, you would have factored the top and bottom. Then you would have canceled, and then you would have said, what, plug in 2 and you get 4, right? I'm going to address your frustration in a second, because I know you're somewhat frustrated. Okay, this example. Limit x goes to 0, tangent 6x over sine 3x. Now, do y'all remember how we would have done this before? This was that problem where I showed you how to like pull everything apart, and then it's like we could really use a 3x there, so we make it appear, and then we have to start sliding things around. Remember that? Okay, well, let's check the form first. What's tangent of 0? 0. What's sine of 0? So do we have an indeterminate form that we can apply L'Hopital's rule to? Yes. So I'm going to come in here and apply L'Hopital's rule. Limit x goes to 0. I just need the derivative of top and bottom separately. So what's the derivative of tangent x? Secant squared, sorry, I said tangent x. Secant squared 6x. Careful here now. Chain rule on the top. Times 6. Good. Everyone understand that you took the derivative of tangent to give you the secant squared 6x, but then you go inside and take derivative of 6x, which is 6. All over cosine 3x times 3. Now, go ahead. Try it. Remember, secant is 1 over cosine, isn't it? So what is secant of 0. Well, cosine of 0 is 1, isn't it? So secant of 0 is 1. 1 squared is 1. So you get what on top there? 6. And then again, cosine of 1 on the, cosine of 0 on the bottom is 1. 1 times 3 is 3. The answer is 2. Isn't that nice? How about this one? This is one that I asked you to memorize. Every calculus student should know this. Limit x goes to 0, sine x over x is 1, right? I just told you that. I said take it on faith. And I said if you wanted to know why it's true, you could come by my office. I could prove it to you. And there's a real long proof of it. But once L'Hopital came up with this rule, it's simple. Because this does go to 0 over 0. But by L'Hopital's rule, I can just do derivative of top and bottom and get what? Cosine x on top and on the bottom 1. And what's cosine 0? 1. 1 over 1 is 1. I kind of already know what you're thinking, but I have a good answer to some of your questions that I think some of you are toiling with in your minds. How about this one? Limit x goes to 0, x cubed minus 4x squared minus 3x plus 1 over x to the 4th minus 5x squared plus x. So where's that headed, first of all? Shit, hold on. I meant to go to infinity. Pardon me. Sorry. I meant to go to infinity. The numerators become infinite, denominators become infinite, so we've got infinity over infinity, right? Can you use L'Hopital's rule if you have infinity over infinity? Yes. All right, so I come in here with L'Hopital. And I get 3x squared minus 8x minus 3 all over 4x cubed minus 10x plus 1. Infinity over infinity. So you might be thinking to yourself, well, shit, that didn't help, right? But the great thing about L'Hopital's rule is that you can continue to use it until your limit becomes something you can evaluate. As long as the next step down gave you infinity over infinity again, you can go again. So we go L'Hopital again. So I'm doing a second application of L'Hopital's rule. 6x minus 8 over 12x squared minus 10. What am I getting here? Infinity over infinity again, right? Do it again. Does everyone have that written down? I've got to move to a new page here. Everyone got that? Okay. So I was at limit. So here comes L'Hopital. So it's going to be limit as x goes to infinity. What was it? 6 now over what? 24x? Is that it? Yeah? Y'all agree? Now what do we have? That's right. We do not have L'Hopital anymore, okay? Because what we have now is fixed over infinity. And where does fixed over infinity go? 0. So the good news is you can use L'Hopital over and over and over. The bad news, you have to be careful. You can't just like beat this thing to L'Hopital death, right? You can't just be like L'Hopital. And I mean, like if you went L'Hopital's rule one more time, what would you get? 0 over 24? Now, that would have been correct. You would have got the right answer, but it would have been wrong to use L'Hopital one more time. You can only use L'Hopital when you've got 0 over 0, infinity over infinity. Is that okay? It's a great rule, isn't it? Isn't that nice? Isn't that nice? So if L'Hopital's rule is so nice, why did we torture you with limits? Kind of. There's something else. Because I think a lot of people, like, I don't know if that's what some of y'all were talking. It's like, what the hell didn't you show this to us to begin with, right? This makes some very hard limits easy. There's a reason. What's that? Okay. You need the derivative to do L'Hopital, right? So where did the derivative come from? A limit. Okay, so we had to develop the idea of the limit first. From that came the derivative. Then we can use the derivative to come back and do limits. I couldn't have walked in here first day and been like, okay, we're going to do some limits. This is L'Hopital's rule. Take derivative top and bottom. You mean, what the fuck? What's a derivative? You know? You know what I'm saying? Like, you wouldn't have known what a derivative is. Follow me? So it's kind of like getting the horse in front of or the carriage in front of the horse here. We couldn't do that. But now we have this. It's a great thing. Let's try this. How about limit x goes to infinity? Ooh. Okay. X to the 100th power over e to the x. So where does the numerator go? What's infinity to the 100th power? Infinity, right? What's e to the x? So e to the infinity. Now this is where I asked you, 3.1, the video, I showed you what e to the x did, right? And as you go to infinity, e to the x goes to infinity, doesn't it? So we have infinity over infinity. So we're going to use L'Hopital's rule, aren't we? So when I use L'Hopital's rule here, I go x to infinity. What do I get? 100 x to the 99 over e to the x. What's that? I'm subtracting 1 from 100. 100 minus 1. Where does that go? Infinity over infinity, right? So I do it again. What would the next line be? It'd be 100 times 99 times x to the 98 over e to the x, and it would be infinity over infinity again. So what? You can see, we're not going to be able to do this by hand, but we can get to the answer by thinking it through. Every single time we apply L'Hopital's rule, what happens to the power of the numerator? It comes down by 1, comes down by 1. What happens to the denominator? Stays the same. So eventually, right, with enough applications of L'Hopital's rule, right, eventually what I'm going to get is a limit, x goes to infinity, of eventually a constant, right? Because eventually you'll have some number times x, right? And then the next time you take the derivative, it'll just be a number on top, won't it? A number over what? E to the x. And when you take that, it's going to be fixed over infinity, won't it? And it's going to go to 0 then. It would basically turn into a factorial. When you get down to the very end, it'd be 100 factorial. over e to the x. So it'd be a number over e to the x. You don't need to say what it is. You need to understand that every application of L'Hopital brings your degree of your numerator down by 1. But it is a factorial. The number that'll be out there will be a factorial. 100 factorial. Yeah. Well, so are we saying basically that I could have made this x to the 1 bagillion, gazillion, ganillion? Right? Like, what's the limit of that? It's still 0. Because eventually, the power of that numerator would come down in the denominator. What this is saying is this. This is actually pretty amazing. It's saying that if you take x to any power, I don't care what it is, x to the billion power, and you divide it by e to the x, and you look at them as they go out to the right, eventually e to the x gets so big that it smashes this whole thing down to 0. Now, you would think x to a huge power, like x to the billion, gazillion, whatever, is just, it's going to take off, right? And yes, maybe in the beginning it would be bigger than e to the x, but if you go out far enough, eventually e to the x overtakes it and just wipes it out. So e to the x grows fast, exponentially fast. So all exponential functions with a base bigger than 1, like e is base 2.718, something like that. Any exponential function with a base bigger than 1, if you were to compare it to any power function, x to a power, exponential functions eventually just explode compared to power functions. Power functions get big, but nothing like exponential functions, which is why they always say exponentially, it's growing exponentially. That's like people trying to say like so freaking fast that you can't even understand how fast, you know? That's what it is. All right. Okay, so every problem I've presented you with up to this point, we've had one of two things. 0 over 0 or infinity over infinity. But there were all those other ones, right? So let's take a look at some of those other ones. Limit x goes to 0 from the right of x natural log x. So x is headed to 0, right? So what is this first guy headed towards right here? It's headed to 0, right? Times. Now, where does natural log go? What does the natural log function do as you head towards 0? This was in my 3.1 videos also. What does natural log do? As I head to 0. It goes to negative infinity, right? That's the natural log function on the right in the red. As I head towards 0, right, from the right side, as I head towards 0, where does it go? Down to negative infinity. So what I have here is something that's trying to be very small, 0, times something that's trying to be very big but negative. That's like 0 times infinity. And that is an indeterminate form, isn't it? So this is an indeterminate form. So like question marks everywhere. Like what? I don't know then. I got to do something, right? L'Hopital is useful, but only if we have what? You got to have fraction. Infinity over infinity or 0 over 0. You've got to have that. Okay? If you don't, you can't use it. Go with me? Okay. Now, I need to somehow try to manipulate this. And this is the rule of thumb. It will always work, okay? Anytime you have 0 times infinity or 0 times negative infinity, it does not matter. every single time you have that situation, you can always take one of the two products, one of the two factors, and drop it down to the denominator. And when you do that, you will create a fraction, and you will create either infinity over infinity or 0 over 0. So just follow me out here first. I'm leaving the natural log x on top, and I'm dropping the x that was in front on the bottom. But I can't just put x on the bottom. I have to write it like this. Right? Because 1 over x written on the bottom like that actually means x on top, doesn't it? But see, I've created a fraction now. So it's just a clever way to work around our issue. So I would like for us to focus on the blue and yellow separately now and let x go to 0 again. If x goes to 0, where does the blue go? Negative infinity, right? Now focus on the yellow. You get 1 over what? 1 over 0, which goes to either infinity, negative infinity, or does not exist, right? Right? Well, if you work that one out, and you could actually even just draw the graph of 1 over x. This is what 1 over x looks like. Okay, that's the graph of 1 over x. So if I come in from the right, where's it headed? Up to infinity. So this one would actually turn out to have an answer of infinity. Now do you see we have infinity over infinity? Want to see that? So now I can apply L'Hopital's rule. L'Hopital. L'Hopital. Oops, I'm going to have to go to a new page. Did that not do a new page? There we go. Limit x approaches 0 from the right. I think I zoomed. Of, what was it? Oh, here's my L'Hopital. What is the derivative of the top? It was the blue one, right? It was just 1 over x, good. Over, now the derivative of the bottom. Be careful, because what was the bottom? It was 1 over x, right? I want the derivative of that. We're not going to do quotient rule, okay? We're going to bring that x up and make it x to the negative 1. And then take its derivative, which gives us negative x to the negative 2. Yes? Which is really just negative 1 over x squared. Agree with all that on the side? Okay, so my new denominator is negative 1 over x squared. And that's a fraction over a fraction, isn't it? So I can flip it. Oh, sorry, no L'Hopital. I'm not doing L'Hopital. I'm just doing some algebra. This becomes a negative, and then isn't it just x squared over x? Isn't that just x squared over x? And what is x squared over x? Just x, negative x. So what's the limit as x goes to 0 of negative x? 0. So the answer was 0. Ask questions if you have them. Do what? Say again? As soon as you let x go to wherever it's going and you can determine what the answer is, you do not write the limit anymore. So let's see if anyone can regurgitate what I just said. Anytime you see 0 times infinity, what can you do? You turn it into a fraction, right? How do you turn it into a fraction? Drop one of the two, right? You pick one of those two and you drop it down. And when you drop it down, it actually becomes 1 over it, right? So if you pull an x and drop it to the bottom, it becomes 1 over x. If it was an x squared, you drop it to the bottom, it would become 1 over x squared, right? Now, let's kind of revisit this one a little bit. I had limit x goes to 0 What the hell happened? Goes to 0 from the right. I had x, natural log x. And I said, okay, that was 0 times infinity or 0 times negative infinity. And then I said I got to drop something. So I chose to drop the x, didn't I? You could have dropped the natural log. But let's just see what would have happened if I would have dropped the natural log. The x would have stayed on top, and what would I have on bottom? 1 over natural log x, right? That's what I would have. So I would have these two functions, what I'd be looking at. Where does the blue go as x goes to infinity? Where does the blue one go? Let x go to 0. Just the blue. 0. Okay. Now the yellow one. Natural log of 0. Where was that headed? Negative infinity. 1 over negative infinity. Well, fixed over infinity goes where? 0. So we'd have 0 over 0 here, wouldn't we? So this would give us 0 over 0, which is what we'd need for L'Hopital. The problem is that L'Hopital isn't as easy this way, because what's the derivative of the top? 1, fine. But derivative of the bottom? Quotient rule. You'd have to use quotient rule on that. Whereas in the previous, the way I chose it, the bottom, the derivative was just this piece right here, which was fairly easy. So you can grab either one and do it, but sometimes one is better than the other. I hope you followed what I was just saying. Let's try another one. Limit x goes to Okay, let's do it. X goes to 0 from the right again. Square root of x times natural log square root of x. What kind of form do we have here? What's the square root of 0? 0. So this is headed towards 0 here. This is headed towards 0. Natural log of 0, that means what's happening is natural log is heading towards 0? Negative infinity. So this is exactly like the previous problem, isn't it? This is like x natural log x. I just changed it to square roots instead. So what should we do? We're getting 0 times negative infinity, so what should we do? Move the square root of x down. Okay, so I should write natural log square root of x over 1 over the square root of x. Now you don't have to check this, but that is going to give you infinity over infinity. It will. You can go straight to L'Hopital at this point. And what is the derivative of natural log of the square root of x? 1 over the square root of x times, so that's the derivative of natural log of junk, right? Good, 1 over 2 times square root of x. So now that's the derivative of the square root of x. All over, now I need the derivative of the bottom. Now, if I were doing this problem, I would have looked at this as being x to what power? Negative 1/2, right? And then taking the derivative of that. What's the derivative of this? Negative 3 halves. Everyone see what I'm doing? I'm going to take that derivative on the bottom, put it on the underneath over here. But I'm trying to avoid quotient rule, okay? If it's a power of x, just write it as a power of x. 1 over the square root of x is the same as x to the negative 1/2. Now 1/2 comes out, subtract 1, get that. So isn't this now negative 1 over 2 x to the 3/2? That's this, rewritten. Follow? Questions? Questions, comments, concerns, gripes? Hey, what was that numerator, that red up there? What's 1 over root x times 1 over root x? Because you can multiply those across, right? 1 on top and then 2 times what? Kevin, you're multiplying. Just 2x. It's just 2x. So you have on the top limit, x goes to 0 from the right, 1 over 2x. But then the bottom one, can I flip it and bring it up? Come 2x to the 3/2 over negative 1. So I took that blue fraction, flipped it up, and I put the two red ones together. And I think I get some cancellation here. 2's go away. What's x to the 3/2 over x? X to the 1/2. And I had a negative 1 down there, right? So I have an x to the 1/2 on top, and I have a negative 1 on bottom, which is basically square root of x over negative 1, which is negative square root of x. Now let x go to 0 now. All that for nothing. Literally nothing. They're not all going to come out to be 0, okay? I'm not going to work this one out. I'm just going to try and help you set it up. What if you had limit x goes to infinity of x squared e to the negative x squared? Where does x squared go? Infinity? Where does e to the negative x squared go? You gotta be a little careful with that one. Think about this. Isn't this the same as 1 over e to the x squared? Remember, negative exponent means drop it down, doesn't it? So e to the negative x squared really means 1 over e to the x squared. That one is fixed over infinity, isn't it? You get e to the infinity squared. So that actually goes to 0. This goes to 0, and this one goes to infinity. So if I were doing this problem, I would choose to drop the e to the negative x squared down, and it would just be x squared over e to the x squared. See, you wouldn't even need to write 1 over it. Because it already has the negative exponent, you could just drop it to the bottom. So these are the same exact problems. And now you have infinity over infinity, and you can apply L'Hopital. Y'all doing all right? We're almost there. Almost at the finish line here. How about limit x goes to infinity? Shit. Sorry, that's not what I meant. Yeah, what the hell? Let's do it. X goes to infinity of 1 plus 1 over x to the x. I'm going to put a red star next to this one. This is a classic example. Classic meaning like every Cal 1 student should see this problem, I think. And you'll see at the end why it's so important. What is the form we have? What does the base want to become? So when you're looking, when I say base, I'm saying, what does the yellow want to become? 1 over infinity, right? 1 over infinity? What's 1 over infinity want to become? Close to 0, right? So I'm saying this part right here, right? 1 over infinity wants to become 0. But then add 1. What's 0 plus 1? 1. So the base wants to become 1, doesn't it? Raised to the what? Infinity. Is 1 to the infinity an indeterminate form? Yes. The base is like, I want to be 1, right? The exponent's saying, I want to make you huge. So who wins? Who wins this battle right here? We're about to find out. Now, we have seen 0 over 0. We've seen infinity over infinity. We've seen 0 times infinity. We have not faced this yet. And so there's a whole different attack for this one. All right, so here it comes. The first thing you do whenever you see something like 1 to the infinity, or if you see like infinity to the 0, all the indeterminate forms that we had where there were exponents involved, right? Any of those, here's the first thing you do. You say y equals the limit as x goes to infinity. So what I'm doing is I'm creating an equation, and I'm just saying, hey, look, everyone, I would just like to know what y is, okay? Can you just tell me what y is, please, right? Before it was just, what's this limit? Now I'm saying, call it y. But by creating an equation, what do you think it is that I'm going to be able to do? Take the natural log on both sides. So I'm going to take the natural log on both sides. What is that going to allow me to do on the right side? Well, let me do it this way. The natural log we call it pass through the limit, meaning that the natural log can go through the limit. Algebraically, it's fine to do that. So I've taken the natural log on both sides, and that allows me to do what now? Take that x and drop it in front of the natural log. Freaking fabulous. Let's see what happens here. Limit x goes to infinity. X natural log 1 plus 1 over x, and no more power on it. Now let's all kind of take a step back and take a breath. What we did before this, before we took our break, right, was I taught you logarithmic differentiation, right? That was how to use logs to take derivatives, right? This is not logarithmic differentiation. This is us trying to figure out a limit and using the property of logs to find the limit. We are not going to come through and draw a squiggly line and take derivatives of both sides. That's not what this is. All we have to do is figure out what that limit on the right is. See, what is this? Do you notice now that we've turned this into a product? Right? That's a product, right? So where does that first part of the product go right now? Take the limit. What does x do as x goes to infinity? Goes to infinity. Okay, times, what did we say this was going to in here? What's 1 over infinity? 0, and then plus 1 would be 1, right? So the inside there is trying to go to 1. What's natural log of 1? 0. This whole thing goes to 0. So what do we have? Infinity times 0. What do you do whenever you see infinity times 0? What? Take one and drop it. Exactly. Which one looks like the better one to drop? The x. Okay? So watch how I write. Notice I'm not going to get lazy in my writing. Natural log y equals limit x goes to infinity. I'm going to leave the natural log of 1 plus 1 over x. But then on the bottom, I'm dropping the x, which means it's a 1 over x on the bottom. Now, I'm going to just double check this. What is the numerator going to? So 1 over x goes to 0, right? That goes to 0. Can you all even see that dot moving?
Yeah.
Barely. That goes to 0 plus 1. That goes to 1. Natural log of 1 is 0, right? Okay. Now on the bottom, fixed over infinity goes to 0. So now we have 0 over 0. L'Hopital. So we went from this crazy form, which was where it was the beginning of this. It was 1 to the infinity. We said, okay, make an equation. Natural log both sides. Pull that power out. Now we have infinity times 0. Okay, good. We can drop 1. Now we have 0 over 0. Good. L'Hopital. So the way we write this is as follows. Natural log y equals, with L'Hopital, limit x goes to infinity. Now I have to do the derivative of the top and the derivative of the bottom separately. So what's the derivative of natural log of junk? So 1 over the junk times now the derivative of the junk, right? What's derivative of 1? 0. What's the derivative of 1 over x? Negative 1 over x squared. Very good. Right? That's x to the negative 1. 1 over x is x to the negative 1. Derivative of that is negative 1 x to the negative 2. That's negative 1 over x squared. So you remember how I told everyone here should know the derivative of square root of x is 1 over 2 root x? Everyone here should know the derivative of 1 over x is negative 1 over x squared. It just comes up a lot. That's just the derivative of the top, right? Over the derivative of the bottom. What's the derivative of the bottom? Negative 1 over x squared again. Hot damn, that's beautiful. Because what happens? They cancel. That's great. That's great. You'll have that written down? I'm not done with the problem. I got to go to a new page. Any questions? I feel like you're burnt out. Oops. What the hell? Why can't I get a new page? Oh, I ran out of paper. My computer ran out of paper. That's not a good thing. That means I've gone past. It's weird. Okay, so here's where I am. Natural log y equals limit x was going to infinity. The only thing left was a 1 over 1 plus 1 over x, right? Everything else canceled? Let x go to infinity now. What do you get? 1 over 1, which is 1. So here's what we're saying, folks. The natural log of y equals this limit, but that equals 1. So our answer is 1? No. What did I say in the very beginning? What's y? It's like I'm asking you what, in the very beginning I'm asking you what y is, and you're telling me what natural log of y is. That's not what I asked for. So how do you get y out of natural log? E on both sides. Good. So now I'm just going to take e on both sides. The e in the natural log will kill each other off. That's why I'm using it. So I get y equals what? E to the 1, which is just E. So the answer is E. So in summary, if I write down limit, well, I'll write it backwards. I'll put my answer first. E equals the limit as x goes to infinity, 1 plus 1 over x to the x. Really cool. So there's like, remember I told y'all about that e to the pi I plus 1 equals 0. Did I show y'all that? Did I show you? No? Sorry, wrong semester. I'm thinking up here. I never showed y'all that? Maybe I did and it's gone already. That's argued to be one of the most beautiful equations in math. No? E to the pi I plus 1 equals 0. Widely considered one of the most beautiful equations in math. The reason is because it contains all of the most important numbers in math. 0, which everyone doesn't really think is a big deal. But remember how I told you, like, next to everything is a hidden 0? You can always add and subtract something. I told you that was a pretty high-level thought there. So 0 is an important thing. 1 is an important thing. Obviously, 1 is important now. I, the imaginary unit, that I up there, I is the square root of -1. Pi is the ratio of a circle's circumference to its diameter. And then E, which is the base of the log function that is special because the E function is its own is the only function that is its only is the only function that its derivative is itself. Okay, but the definition of E is this. Like, you know how E is approximately 2.718 blah blah blah. Anyone who has a calculator, you don't have to do this now, but if you're interested, just take some numbers for x and plug them in. Like take 10 and plug it in. And don't worry about the limit here. Just do 1 plus 1 over 10 to the 10. And then do 1 plus 1 over 100 to the 100. And then get bigger and bigger numbers. And I promise you, the further you go out, the bigger your x gets, the closer you get to E. E is approximately 2.718, but E goes forever. Never stops, never terminates, never repeats. So if you want to know what E is that. E is if you could go forever, that's E. Kind of interesting concept. How many of you kind of recall this formula from college algebra? You may have seen this. This is a formula for compound interest, okay? And what they said was this. They said, look, R is your interest rate, okay? T is the time, how long you're going to leave the money in the bank. And N, hold on. I messed up the formula. It's N down here. And N is the number of times they compound the interest per year. So like if you put your money in a bank and they say, okay, we're going to give you 2%, that's really high, but 2% for your money, and we'll compound the interest monthly. What that means is that they take your money and they cut it into 12 pieces, and every month they give you interest on a 12th. Then the next month, an interest on that. If you compound it daily, they take your money, they cut it into 160 or 365 pieces or whatever, and they give you interest on that piece every day. Well, what if you could cut your money up into an infinite number of pieces and give you interest on it every instant in time? Well, that would mean let n go to infinity here. Let the number of times you cut it up and the number of times you compound it go to infinity. And guess what that friggin' looks like? 1 plus 1 over x to the x, right? Replacing this n with x's. You get that, don't you? So a lot of you learn this formula right after you learn that one, PERT. And all PERT is letting n go to infinity in that formula. And when you let n go to infinity, you basically turn it into e. But that's beyond the scope of this class. I just wanted to like show you like it's used all the time. Okay, that limit is used, and whenever you use that limit, it basically turns it into e. All right. I think we're. Do you feel like done? Do y'all feel done? Maybe. Man, what do y'all want to do? Well, 15 minutes, right? That's all we have? Yeah, that's good. I think we're done. Let's review back what our homework is. It's a lot of work right there. That's what, like 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, maybe like 30 or 40 problems right there. It's a lot of work. So enjoy. Do y'all want to have a quiz next time, beginning of class, or? Sure. See, the thing is, the quizzes help you if you're ready for them. If you're not ready for them, but the thing is, you have to think about what your grades are on your quiz right now, because we're in week 5. We only have what, like 2 more weeks after this, or 3, right? So we're running out of quiz chances. The quizzes are what, like 20 or 30% of your grade? 30 to 30. So if you stick with what you've got as quizzes, it could really hurt you. So you might want to actually be asking for quizzes at this point, because the more you have, the more maybe I can drop 1, maybe 2. You know what I'm saying? So let's plan on a quiz beginning of class over these problems. I'll just do something similar to what's in there. Don't come in here like, oh man. He's right here. Your quiz will cover 1 problem from each section. 1 from 3.3, 1 from 3.7.
I was wondering if I could get 3 and 4.
Chapter 3 and 4, yeah. Let me turn off my camera first.